This is a video to just quickly summarize the general mechanism of reaction for substitution at a carbonyl carbon. So here we have a simple carbonyl compound and ester. This is actually methyl ethanoate, and let's have it be attacked by a pretty simple nucleophile, our hydroxide ion. It is a nucleophile, so it's looking for something that probably has a little bit of positive charge to it. And always remember our carbonyl carbon right here is going to have a partial positive charge because it's bonded to an electronegative oxygen. So that makes it electrophilic, and that makes it attractive to the nucleophile that's attacking. The nucleophile donates 2 electrons to start making a bond with the carbonyl carbon, and the carbonyl carbon needs to lose a bond, and oxygen up there takes those electrons that were in the bond all to itself. And now we have formed the tetrahedral intermediate. Notice what we started with was a planar molecule. The carbonyl carbon was bonded to 3 areas of electron density, and all the bond angles were 120 degrees. But in this intermediate that we formed, the geometry is tetrahedral. We have 109 degree bond angles, and the molecule is 3-dimensional. The geometry around the carbonyl carbon is 3-dimensional. Once this tetrahedral intermediate is formed, the leaving group leaves, and the group that leaves is the weakest base. So it's pretty much never the CH3. It's not an alkyl group that usually leaves. It's something that can be somewhat stable on its own with a negative charge. In this case, it's going to be this methoxy group that will leave and form a methoxide anion. And that's kind of pushed out a little bit by the fact that this oxygen kind of wants to not be negative, and it wants to share its electrons with the carbon again. So as this double bond to the oxygen starts to form, the weakest base, the leaving group, gets kicked out. And now the substitution is complete, and we have planarity around the carbonyl carbon again. And here's almost the same story again, but with a neutral nucleophile instead of an anionic nucleophile. Simple example, water. Same thing happens at first. Nucleophile attacks because that is a partially positively charged carbonyl carbon. The second bond there breaks, and right after that neutral nucleophile makes a bond, it has a positive formal charge right here. And from the way it looks now, that group that just came on looks like a great leaving group, because right now we could just reverse what we've done already and pop off of water and it would be pretty happy. So there's another step that happens here. Oops, forgot my methyl. That's been there. That was there the whole time. But this extra step is to deprotonate the group that got added. So that nucleophile is going to encounter some kind of base, we'll just call it B, which is going to donate some electrons and pop off an H+. And now we have a tetrahedral intermediate where a group other than the nucleophile that just attacked is going to come off. Because losing this hydrogen here turned this from a very good leaving group of water into a kind of bad leaving group, which would end up being an OH- if it came off. So again, this this OCH3 over here is the best leaving group on this tetrahedral intermediate. So So again, the last step is for this negatively charged oxygen to try to share its electrons, and as this carbon gains an extra bond, it kind of helps ditch the leaving group, and you get your final substituted product.